Welcome to this jam session, and in this jam session I'm going to show you how the principles of functional programming that we have seen in the course for Haskell can be applied to the language Kotlin. Kotlin is a language designed by JetBrains, and if you're an IntelliJ user like I am, you can download the plugin for Kotlin and play with it. So let's go and see how we can do functional programming in a normal language. Here is the main function for our Kotlin program. Just like Java and C#, main takes an array of strings as an argument. And then inside the body, we see a couple of expressions here. And I want to walk you through them and show you how this relates to the Haskell code that we have seen. And note that for me, functional programming does not imply not using side effects. Functional programming does not mean using pattern matching. For me, functional programming means using higher order functions, whether they're pure or not, and focusing on expressions versus statements. And in Kotlin, you can define mutable variables, so I can define var y and initialize it to 1, and then I can say y plus equals 1, and this just works. And I have no problem at all with that, okay? But what I wanted to show here is the functional programming features that are supported by Kotlin. So let's look at this first statement here. So I define a immutable variable here, or just a name, square, and that calls the function foo. And foo is defined here as a function, and you see the if I hover over this, that's maybe a little bit small to see on the screen, but Kotlin has type inference for the return type, so here it said, like in that very small yellow thing that you couldn't see, that the type of foo is a function that takes an int and returns an int. And here I call foo of 42, and I print it. Now another thing that we've seen in Haskell in the list comprehensions were these range expressions where we could write in Haskell square brackets, 1 dot dot n. Kotlin supports something very similar, so I can say for x in the range 1 to 5, print x. So here you see that this same kind of syntax and ideas of range comprehensions appear in other languages as well. Now, the next example shows some higher order functions and the syntax that Kotlin uses for them. So here I declare a list of the values 1, 2, 3, 4, and then I map the function a arrow, the lambda expression a arrow, a times 2 over it, and then I filter out all the values less than 5. And you see that there's two ways to define a lambda expression. The first one here is where you name the argument and arrow and then the expression body. The lambda is enclosed in curly braces. You can leave out the parens around the map, but I kind of like that to put them there explicitly. And here in the filter you see that if a lambda expression just takes one argument, we don't have to name it, and we just call it it. It's very similar to when you have an object that the implicit context, the this parameter is called this. When you have a function with one parameter, it makes sense to call that one parameter, give it a special name, such that you have to write less. Okay, so you can do everything that you learned in the course with map, filter, fold. You can do in Kotlin as well. And you see here, there's a lot of functions defined on lists that you will recognize from the Haskell prelude. So most programming languages, if you look at the APIs for collections, they are very familiar, and they all contain the same higher order functions. Sometimes the names are slightly different, but in general, that should be very familiar. One nice thing that Knotlin has, which C# also has, are extension methods. So in this case, I define an extension method sum on integers. So let's look at the definition for the sum extension method. So here you see I'm defining a lambda expression, and this int dot there indicates that sum is an extension method on int, and it takes a parameter, let's call that other, and it returns an int. So here you see the type, and then the body of the extension method just adds this to other. So in this case, this is in scope and ranges over the receiver. And I think this is also quite nice. It's less verbose than the way you define extension methods in C#, where you have to define a static method, you have to explicitly name the parameter, put a this modifier in front. This is very, very concise. And then we can just call one dot sum of two. In the lectures, when we talked about defining data types, I compared Haskell algebraic data types with classes in object-oriented languages. And it's worth emphasizing that if you look at the correspondences, if you look at what is similar, a Haskell algebraic data type is really a kind of streamlined way to write a class hierarchy with constructors and so on. And pattern matching is really a streamlined way to do is checks. And let's see how we would define the type of lists in Knotlin, and how we can define one of the standard recursive functions over lists as an extension method using pattern matching or is-test. And then you will see that there's a little bit more syntax than in Haskell, or maybe even the same amount of characters. But the important thing here is that you can take the concepts from Haskell algebraic data types and apply them in an object-oriented language, and vice versa. If you have an inheritance hierarchy in an object-oriented language, you can often model that also using Haskell algebraic data types. Here is the type of lists. So what I do is I define an abstract class list, and this data modifier is a special modifier that you can put on a Knotlin class that will make sure that a bunch of things are implemented, like equals, hash code, and so on. So that's rather easy. And then I define two derived classes. So in Haskell, these would be on the right-hand side of the algebraic data type. So nil is a special case of a list, and cons is a special case of a list that has a head of type T and a tail of type list of T. Okay, so as you can see, if you squint through it or you put on some different color glasses, this class declaration is isomorphic to the Haskell definition for lists. One important difference, of course, is that Knotlin is a strict language, so these are not lazy lists. So if we want to do lazy lists, we have to do a little bit more work, and we have to make sure that the tail remains unevaluated, and one way to do that is by creating a thunk for that, but that's a topic for a different time. Now let's look at how we define a function recursively over this new list type. So here we define length, and length is defined as an extension method over list. So you see that list here has no methods, but I just define them outside. And here's my pattern match, and I check when this is nil, the result is 0, and I should line this up properly. So when the list is nil, the length is 0. That's exactly like in Haskell. And when we have a cons, what I do is the result is 1 plus the length of the tail of the list. Okay? And so instead of pattern matching to get at the tail of the list, I am calling here the accessor to get the tail. And since the Knotlin compiler cannot determine that I'm not extending this data class anymore, I have to put here this spurious else clause to throw an exception, but we know that this will never happen. But if we do this, if we don't do this, we will get an error here and say that an else clause is required. Okay, and then we can create a list here. You see, it looks very similar to Haskell. We use named arguments here. We create a list that just contains the value 3, and then we calculate this length. So let's run this code to see if everything I told you is actually true. So there we go. Let's run it. There we go. So going from top to bottom, this one here is the length of this list. Well, the list contains only the value 3. So there we go. If I compute 1 plus 2, that is 3. If I take the numbers 1 to 4 and I double them and then filter out the ones that are less than 5, I get the list 2, 4. If I print the numbers 1 to 5, I get the numbers 1 to 5. And if I square 42, I get 764. So there we go. Programming Knotlin. If you want to learn more about Knotlin, you can go to the Knotlin website. And you can jump in immediately using all the skills you learned in the Haskell part of this lecture. Thank you very much, and see you next time.